Hello, this is the third session of the Quantitative Tuesdays, and today we will talk about univariate analysis and how we can develop certain models with one single variable to use forecasting techniques subsequently. Today's topics will cover an introduction to univariate time series and lagged variables into the equation. Basically, if we have one variable, then we can use its own past to sort of foresee its future. Then we can learn a bit about how to develop autoregressive models or moving average models and the difference between them, and how we can combine the two in sort of autoregressive moving average modeling called ARMA. Then we will look into forecasting, and we'll also go through a bit of unit root testing and what it is about. What we did last time was panel data, and we looked at a lot of different types of cross-sectional data. And we looked at how we can use categorical dummy variables in panel or cross-sectional data to use data which is quantitative, which is qualitative in nature for quantitative analysis. Today we are doing something completely different. We have a very quantitative data series which we will examine, and it's one data series, so that's why we call it a univariate time series analysis. So we have one data series over an extended period of time. It could be daily, it could be by the minute, every 10 minutes, it could be monthly, quarterly, even annually. So, for example, examples of time series data would be annual GDP of the UK since 1950 to 2020, or David's weight measured at the start of every month for 10 years. So if we had data for that, we could conduct a time series analysis of that, or daily prices of Bitcoin, for example, and so on. So these are all individual univariate time series, and this session is about univariate time series and how we can use one variable over time. And in the next one, we will talk about multivariate time series, but to develop further into that, it's a good idea to have a look at this aspect of time series as well. So this is basically what it is. Univariate time series is just one single variable over time. And multivariate time series is looking at the simple panel sort of regression, but across an extended period of time with more than one variables. And there are some more complications to that, which we will study in next Tuesday. Because if you are looking at two variables over an extended period of time, time is a variable which can determine both of them, and they might not have any relation with each other. So, for example, you are looking at the per capita GDP growth rate of the United Kingdom, and you're comparing it with let's say population growth rate of Uganda, then when you conduct a multivariate time series analysis, it's very likely that you will get very strongly statistically significant coefficients, but it does not mean they have an actual association with each other, or that one determines another. Those kind of regressions are called spurious regressions, which we will talk more about next time when we get into multivariate time series. For now, we will talk all about univariate time series. When we talk about univariate time series, as I mentioned, we can use a technique to basically use one variable and extract more variables out of that one variable, and those extra variables are just the same variables past values. So for example, if we have a variable, let's call it xt, which is a vector of variables for, now these could be, let's say, the prices of the daily prices of Bitcoin, for example. So xt minus 1 would be the same daily prices of Bitcoin, but for yesterday. And A is just the constant coefficient. We have the error term in the equation, and then we keep on going with p number of lags. So we have the price for yesterday, day before yesterday, the day before yesterday, until p. And depending on how we structure our autoregressive model, we could have 1 lag, 2 lags, 5 lags, or even 10 lags. It depends. But we can sum it all together and finally write it like this. So whatever the number of p lags, our regression equation can be summarized and written down as follows. We will look at a hypothetical example to understand what this really is. So let's say if we have XT, which is the daily rate of change in Bitcoin prices, not the prices, but by how much does the Bitcoin price change every day. So we might have, like, let's say, an average determinant of how much the prices change on average every day and so on. But this AR1 model also looks at how much did the price change yesterday. And let's say that for whatsoever reason, let's say there's a news in the market or something which says that all of a sudden Bitcoin price increases by 100. So and that's an exogenous shock. It's a shock which is not modeled within this AR framework, but it's a shock that happened and occurred from the outside due to a rumor or a market sentiment, which we have not included in our model, but it's an exogenous shock. And we are trying to capture that shock and the effect of that shock over time using this lagged variable. So let's say that we have a shock to the Bitcoin price by $100. And by that, I mean, let's say Bitcoin prices for an external reason, a reason external to the model, an exogenous shock increases by $100. So if this beta variable is 0.5, it means that because of that exogenous shock, because of which Bitcoin's prices increased yesterday by $100, we can expect the price to increase today by another $50 because beta is 0.5 and yesterday's shock was 100. So looking at that, we can just model this as follows. So, and then we are expecting the price to increase today by $50, tomorrow by $25 because yesterday's shock, half of yesterday's shock was repeated today, and half of today's shock will be repeated tomorrow. So 0.5 times 0.5 times 100 would be $25. And the day after tomorrow, we can expect it to, we can expect the price to continue to increase by $12.5, and then 6.25, I guess, and so on. So basically, using this framework, we know, depending on what the value of this beta is, and it's going to be a number between 0 and 1, depending on the value of this beta is, if the value of this beta is close to 1, let's say 0.9, then yesterday's shock will of $100 will still go on today by $90 and the day and tomorrow by 81 and so on. So the effect of an exogenous shock will prevail and continue to affect Bitcoin prices for an extended period of time. But if the beta is small, then this effect is expected to die off much quicker. In this example, we are just looking at a beta of 0.5. So the effect of an exogenous shock is kind of wearing out over time. In like this hypothetical graph, for example. So well, there are some problems with AR, with the autoregressive model, which we're going to see. Basically, the question is, what if this beta value is either 0 or 1? And that's an interesting case because going back to this equation, the exact same equation, if beta is 0, then whatever yesterday's shock was is not going to affect today's Bitcoin price. So for example, in this situation, if beta was 0, then if there was an exogenous shock affecting Bitcoin prices yesterday, that shock is not expected to affect Bitcoin prices today because the coefficient of the lagged variable is 0, if that makes sense. So what we call that sort of a model, if this is 0, is a white noise kind of a model, which means that there is no way to tell by looking at yesterday's shock that what will be the effect of that today, but the effect that will happen today will just circulate around with some finite variance, some value of some finite variance. It will circulate around alpha, which is the average, and it could be 0, it could be another value different from 0, but it's just white noise, which means that whatever we get is just completely random, and it depends on the variance of the error term, if that makes sense. So in this case, our autoregressive model is not really telling much. It's not explanatory. And on the complete opposite, if beta is 1, which means that if yesterday's shock was 100, today's shock will also be 100, because of which tomorrow's shock will also be 100. What we have over here is that the effect of a shock is not dying off. And if beta is 1, then we have a model where the best guess of what tomorrow's Bitcoin price will be is today's Bitcoin price. And the best guess for the day after tomorrow's Bitcoin price is tomorrow's Bitcoin price. So we have nothing more to say, but if beta is 1 in this case, then we have a random walk, which basically in this case means that if Bitcoin price today is X amount of dollars, then when we are trying to forecast tomorrow's Bitcoin price, our best guess would be the exact same X amount of dollars. And it will have, and depending on the variance, the size of the variance, it could go in any direction. So the problem with that is this kind of a series can go in any direction, because of a shock, if it goes up, it's going to stay up, and then it could keep on infinitely going up or down. That kind of random walk model is unstable, and therefore we cannot conduct a univariate time series analysis using autoregressive models for this situation. So the term which we use in the statistical term which we use is that this series would be non-stationary, which means that it's not stable and it's not stationary around a mean, and therefore it has an infinite variance, which means that it can go up to an infinite amount or just vary to an infinite amount. There is no range to which we could expect. And when we have that, we cannot, but there's a solution to this as well if we have a time series like that, which we will talk about. So basically, why is stationarity so important? And here, back to this model, the left one, even though it's white noise, it's still a stationary series. It's stationary around the mean. And the right one is non-stationary, so we cannot conduct ARMA models for this kind of a series. So why is stationarity so important? To understand that, we need to understand why we need to have beta less than 1, this coefficient value of beta over here. So the reason is that if beta was equal to 1, then we will not have finite variance for XT or Bitcoin prices in our example. So here's the proof of that. We'll take this equation, our AR1 equation, autoregressive equation of lag 1, and we will take variances on both sides to compute the variance of XT. We get the variance of the constant, and the constant does not vary, so that will be 0. And then we get the variance of this term. If we take beta outside, that would be squared times variance of, and assuming that the variance of XT and the variance of yesterday's prices is going to be the same, we can just replace that with XT, and the variance of the error term is sigma squared. So we take XT on the other side, we get 1 minus beta, variance of XT equals to sigma squared. What we get is that variance of XT equals to sigma squared divided by 1 minus beta. And simple calculus, if beta is equals to 1, then variance would be sigma squared divided by 0, which is infinity. So in order for the autoregressive model to be stable, we need beta less than 1 in these kind of univariate models. How can we test for that? There's a very simple tool, and it's available in most statistical packages. It's available in Stata, in eViews. You can do it in R. I'm not sure about SPSS. I haven't used it, but you should be able to. And even then, so this just uses the same regression technique, which we will look at, and you will be able to understand what this is about in a bit. This is not the only one, but one of the most popular ways to test for stationarity in a series is the augmented Dickey-Fuller unit root test. What we have here is that, let's say we take the difference, the first difference, and that means we subtract from today's Bitcoin price yesterday's Bitcoin price. So that gives us the delta, or the change in Bitcoin price over that day. To do that, we do the same on both sides of the equation, so that it's still balanced. And we get delta xt, which is just another term for change in xt over that day, equals to alpha beta minus 1 xt minus 1 plus the error term. Now we will introduce b equals to beta minus 1, so that we have our Dickey-Fuller test equation. We replace this beta minus 1 by b, so that we can conduct these hypothesis tests. If b equals to 0, which means beta equals to 1, then we have xt is not stationary because beta equals to 1. If b is negative, so we will conduct one tilde test. If b is negative, then beta is less than 1. Therefore, xt is actually stationary. So, well, Dickey and Fuller, when they came up with this unit root test equation, they said that the t distribution of this coefficient is actually not normal. So they suggested using McKinnon p-values instead. But this is something that you probably won't have to worry about if you're conducting univariate analysis, because your statistical package should be able to do that. And it will provide the p-values for you. So this is just an insight on how the unit root test actually carries on. So it's just using the same regression techniques just to find out that by these hypotheses, we just want to make sure that beta is less than 1, so that we could carry on with our unit root analysis, with our univariate time series analysis, if that makes sense. Moving on, the same question which was raised earlier. What if the series is not stationary? For example, the random walk series over here. If we cannot directly go ahead and conduct our time series analysis for this one, then we still need to make use of that data. And if it's not stationary, a simple solution to that is we take the first differences. So we construct another series out of this series, which is delta xt. And that is the difference between these daily or monthly or yearly prices that we have, or whatever variable that we have. We can take simple first differences. So the value which we will get will be the dollar change in prices, or we can take the difference of logs. We call it log deviation. If we do that, then what we get is the growth rate, the percentage change. So depending on how you select your model, if you take the log differences, then you get the percentage change, which sometimes is a lot more intuitive. But you can also get the unit change, which will be the change in terms of dollars if you are, or pounds if that's the currency, or in terms of whatever you're modeling, COVID cases, population headcount. So it will be in terms of that. But if you take the difference of logs, then we will get log deviation. Once you take these first differences, you can just, on that new series, you can repeat the Dickey-Fuller test, but for delta xt. Most likely, you will get a stationary series out of that. When you do, after you conduct the Dickey-Fuller test again, but for this new differenced series, when you get stationary results after that, you can say that your original series for xt was integrated to the order of 1, which means that if you difference it one time, then you get a stationary series. But in the unlikely case that you still don't get a stationary series, you can repeat the process again. And you can take the second difference. So you can take the difference of the difference, something like that. Just a notation. So then you will definitely get a stationary series. So then you can say that your xt is integrated to the order of 2, which means that if you difference it twice, you get a stationary series. And we only need that because after differencing it, we can conduct our univariate analysis. Because a differenced series, in this case, a stationary series, might be related to its past values, but it's not really dependent on time. If it's not white noise, it is something like this, circulates around the mean, does not depend on time, but could depend on its past values. But maybe not exactly this graph because this is completely unpredictable, but you can imagine. Okay, something like this, probably. And that tells us that in our auto-regressive model, how many lags should we use? There are ways to, and there's no single way to assess how many lags should we use in the equation. But in some cases, we can just kind of guess looking at the graphs, but a better way to do it would be what we will see in a bit. Like this one, for example, autoregressive model of one lag just captures the shock to the same variable yesterday, or if it's monthly, then the month before, and so on. But this one, if your data series looks like this, your future might not only depend on what happened today, but what happened yesterday, and it might be related with 2 lags, and so on. Okay, that's an introduction for autoregressive models, and now we will look at another part, which is moving average models. And it's a similar idea, but the idea is that what if a shock which occurred yesterday only affects Bitcoin prices today and no further. It just stops right there. So you can say that your series has a short memory. It doesn't have a long memory. The shock which occurred yesterday does not prolong for a very long time. It just affects today's output, and that's it. So in order to model that kind of a scenario, we, instead of looking at the past values of the same series, we can look at what was the error of the previous, which we can look at how much did the previous series deviate from its average. So if the average of a series is 10, but yesterday's output was 12, 2 above the average, then that's the error, because the stationary series is meant to, if the average is 10, then it's meant to fluctuate around 10, but it was 2 units above that. So that's the error, and how will that affect today's output? So we just look at the previous term's error, not the past values of xt. So in MA moving average 1 model, and the reason why it's called moving average is because it's a time series that just circulates around the average, and in many cases the average might be 0, so it circulates around the 0 line, or might be a value different than 0, which is why we include the constant alpha into the equation. And just like the previous AR model, this can also be summarized like this. Okay. So once again, it will depend on how the series is actually structured, that how many lags of the error term should we use to model our time series. Basically, this is the idea. So let's look at a moving average 2 model. Imagine the same Bitcoin example, and this example hopefully should make it clearer, because I can imagine there might be some confusions as of yet. So imagine that if there was a shock, the same shock to the Bitcoin prices by $100, but it's a moving average model and the series has short memory, so the shock affects the series immediately and does not prolong over a long period of time, and that's it. So if that were the case, hypothetically speaking, then imagine the same Bitcoin example where XT tries to model the daily rate of change in Bitcoin prices. In this case, we have alpha equals to 20, which means that on average, daily Bitcoin prices are expected to increase by $20. So this means that on average, they're meant to increase by $20, but for some exogenous reason, for some reason external to this model, Bitcoin prices actually increased by $100 above this 20, which means that at time t, Bitcoin prices increased by $120. So the shock was by an extra $100. So if this is the model, which we gathered out of our estimation from the statistical software. So if this is the model, then the shock at time t is expected to affect the output at time t plus 1 and t plus 2, but that's it. That's where the impact of this shock stops, because we are only modeling error terms with 2 lags, and that's it. And we are not modeling XT's own past values. So the shock almost instantly dies off 2 days later. We can have both positive or negative values for this. So imagine in this situation, there's an exogenous shock and Bitcoin prices increase by $100, which means that for some exogenous reason, Bitcoin prices increase by $100 above the average. And there are day traders who just want to exploit this opportunity and sell. So that's what they do. Day traders cash out the opportunity that brings prices down by $40 below the average the next day. So if the average was 20, $40 below that would take the change in price the next day to minus 20. Low prices encourage more investors. So when it goes to minus 20, the next day, it encourages more investors that bring an increase in price on day t plus 2 by $60 above the average. So 60 plus 20, again, that brings Bitcoin prices, the increase in Bitcoin prices on day t plus 1 by $80. And that's the end of the effect, because after that, we are not modeling this into our moving average model. The effect dies off, and we can expect Bitcoin prices to change henceforth by the same $20 a day, if that makes sense. So this is the main conceptual difference between an AR model and a moving average model in univariate time series. Conceptually, an AR model is where the data series values depend on their own past values, but in a moving average model, deviations from the average, like we saw in this diagram, deviation from the average, current deviation from the average would depend on previous deviations from the average. Okay, and the AR model has the impact of it can prolong for an extended period of time, and it will gradually, slowly die off, like this graph over here that we had a look at earlier, like this one. The effect can prolong and can gradually die off. Now, depending on if the beta is higher, then this can prolong even for a longer period of time. So that's another conceptual difference. But in a moving average model, the impact of a shock wears off pretty much immediately. So that's why AR models are useful if the data series has a long-term memory. It's just a term used which says that the effect is prolonged. And the MA moving average model is useful if the data series has a short-term memory and the effects are immediate short-term. The effect happens the very next day or the day after, or depending on if you're using daily or monthly or yearly, your interpretations would change accordingly and so on. And because of these, sometimes it might be a good idea to explore both aspects. So when we combine both of them together, we get ARMA, autoregressive and moving average model. And this is the exact same equation, but we have combined the autoregressive and moving average components together, which can also be written as this. So we've just, let's say, added this part, the moving average component. And depending on, once again, the data structure, the number of flags for the own variable and the number of flags for the error term would vary. And we would use autocorrelation functions or partial autocorrelation functions to actually determine how many lags should we use, or use some other techniques and so on. So let's look at an example. I've gathered some quarterly data from the Office for National Statistics of the UK government. And this data goes on from 1955 first quarter until the most recent year, 2020, last quarter. And let's analyze this together. I'll show how the data looks like. That's how the data looks like. It's from 1955. It's quarterly data, so every year has 4 data points: Q1, Q2, Q3, and it goes all the way until 2020, last quarter. And the data series that we have is of per capita GDP. All right. For time series, I personally prefer eViews, but I somehow can't access it at the moment. So I'll try to do the same with Stata. But what's more important for this quantitative research method series is the interpretation of what we get. So I'll clear the previous one, and we will import our spreadsheet. There we go. Import variable names as strings. One thing which I find tricky sometimes is that you have to explain your statistical package, that what day or what year is what. So your raw data would look like this. But if you can notice, all of these are in red, which means that Stata doesn't understand what this means. And you have to explain that this is actually quarterly data and this is time. So that can be tricky sometimes. And I just sometimes, for different statistical package, Google it, try to find a way to explain the statistical package, what the data series actually is. So I can generate what a random variable. You can name it date quantitative session 3, just to show how this is not a function, but it's just the name of the variable. And this equals to, I'm trying to explain Stata that we have quarterly data here. And I've named this series quarter. And this series is actually structured as year first, quarter afterwards. And that should explain, so we have a new variable here, which is date QT3, quantitative Tuesday session 3. It's quarterly data. And now I have to explain Stata that this is the time series variable that I want to use for my time series analysis. So we use the command tsset. Now I will use this variable to explain that this is the one I want to use, and this is quarterly. Okay, so that worked perfectly fine. We have quarterly variables from 1955 quarter 1 until 2020 quarter 4. So now Stata knows, if we go to data browser, we have this new variable which we constructed, date QT3. And if you notice, this is the exact same variable, but your statistical package would understand that this is quarterly, and you have to find a way to kind of explain what time of what's the time structure of your time series analysis. And even though they look exactly the same, Stata is just looking at this variable as some text which it does not understand, and looking at this variable, and this is an important point, Stata is now looking at this variable as actual quarterly data series, which it will map against per capita income. Okay, so as I mentioned, there are a lot of different ways and can be complicated depending on if you have daily data, if you have yearly, and the way your data is structured. Sometimes you have gaps, and there are a lot of different ways to fix those as well. But so far, so good. Now we will look at how many lags, as I mentioned, how many lags should we include in our ARMA model. So for that, we can examine, let's say, if we want to look at how many lags should we include for our AR component, auto-regressive component, which means that how many, but wait, before that, I think it's a good idea to actually have a look at how our data series looks like. It's a line, and our variable is per capita GDP. Oh, next variable should be date. Okay. There we go. From the earlier part of this session, if you remember, I mentioned that if our data looks something like this, it might not be stationary. So this just indicates that we might have to work with this data series in first differences. You can do that by conducting, if you want to be sure that this is not stationary, you can conduct one of those statistical tests, which I mentioned, augmented Dickey-Fuller test, or those ones. And there you will find out that this is, okay, time series tests, unit root testing. We are trying to look at per capita GDP. And what we get is, we get a p-value of 0.799, which means that we cannot reject the null hypothesis. In this, the null hypothesis was that beta equals to 1, which means that null hypothesis was that, null hypothesis over here was that we have a non-stationary series which we cannot work with directly. And we cannot reject that, which means that basically we cannot work directly with this series. So what we can work with is we can take the first differences. And Stata, that's pretty simple. You just plot the same, but instead of using per capita GDP, you can put a d dot before that, and that just automatically converts the series into first differences, which looks something like this. So what this means is that every quarter, the amount on the y-axis represents the amount by which GDP per capita has changed over the past, we have 45, 66, over the past 65 years. So that's what it represents. But if you want to look at the same in percentage and how much by percentage has GDP per capita changed, then you can do the exact same thing, but we would have to convert our series in logs. So let's generate a new variable, and let's call it ln per cap, log of GDP per capita, and arbitrarily just choosing a name over here. And this equals to this variable of ours, but the log of it. Okay. And when we plot the difference of this variable, the interpretation that we would get should be in percentage change. What was the name? ln per cap. So now what you get over here, values between negative 0.2 and positive 0.15. These are in percentage changes. So this particular quarter, and we can just easily guess that that was the start of the global pandemic. The GDP per capita for that quarter fell by 20%. And then following that, it went back up again because this is comparing the value of the previous quarter, which was extremely low. So the next one kind of compensated for that And that's how this series works. So I'm guessing that we might also have a moving average component in this because we have some sort of an immediate short-term effect, but we can explore that using ARMA modeling. But before that, we can also look at, and if something's not clear, please note it down. We will discuss it in 5 minutes when we would have the virtual floor open for questions. Okay, so we can graph a partial correlogram. Let's say we want to include 12 lagged variables, and we are looking at ln per cap, the difference of it. So we get a graph like that. So it's trying to tell us that our autoregressive component is significant at the 95% confidence interval for the first lag, and may or may not be for the third lag. It exceeds, so we can try it. We can try modeling with or without it to see which one works better. That's the partial autocorrelations, and we can do the same for. We can do the same as a correlogram, which looks at the error term. So here we have a correlogram, 95% confidence interval. You can choose different ones, and that tells us that we have the very next quarter is where the short-term effect is very strong. So the immediate short-term effect of a shock through the error term, basically the moving average component is the moving average component for one lag should be introduced into the ARMA model. So let's try to model this. We have time series. We can do it from here, and we can try including. So we are looking at ln per capita, but let's not forget the d dot for differences. And if we remember, we had the autoregressive AR lag for the first and the third lag. We can specify exactly which lag and the MA for the first lag. Okay. So let's see how this looks eventually. Okay. What we have over here, now the part of the interpretation, and just remember that your interpretation just very largely depends on your dependent variable. And because our dependent variable is in log deviation, our interpretation would be that this is the percentage effect, which will, so our interpretation would be in terms of percentage changes as well. You have the constant, which is 0.004, which means that by 0.4%, GDP per capita of the UK is increasing quarterly. So the quarterly average GDP per capita growth rate is measured by this, which is statistically significant. And now we are looking at the lagged variables. The first lag is 0.15, relatively small, which means that if there was a shock to the GDP per capita a couple of quarters ago, then that shock is unlikely to continue on affecting GDP per capita today. But the constant is significant, which means that on average, it just somehow fluctuates a bit around this point. But an interesting thing about the moving average component is that it's statistically significant and negative. What this is trying to tell us is that our series over here is mean reverting, and the moving average component is pushing the GDP per capita back to the average, which is the constant over here. So somehow, if for whatever reason, GDP per capita due to an exogenous shock, which happens, and is not a part of the model, is captured through the error term, affects positively or negatively our GDP per capita every quarter, then this component is actually having the exact opposite effect for the immediate next quarter. So basically, because of a shock, if the GDP per capita increased in the previous quarter, then this will have a normalizing effect, and in the next quarter, it would immediately decrease by 40% of that increase in the previous one. So if we have a moving average component like that, the interpretation is that we will get a GDP per capita growth almost always very close to the constant, because the R components are low, and the moving average component is negative, which is pushing which is making our model mean reverting, which means that if there are deviations, the model in the very next period will push it back to towards the mean. So if there's a huge positive shock, the next period, its impact would be 40% negative of that shock. And if there's a huge negative shock, the next period would be 40% positive amount of that shock, and so on. So and you can always try different. So we were not sure if we should use 1 or 3 lags. So you can always just try the model with 1 lag and compare if you get more promising results using that. So I guess it's been confusing, but what we have over here is an ARMA model. If there are any questions, I'll be happy to get them. And we are approaching towards the end. What we have over here, just the last part, is that when we write this equation down, we can use this to forecast the next, let's say, the next 4 quarters. So we can forecast the next 4 quarters using data that we need and data that we have already. To do that, you need what was the GDP per capita growth for the previous quarter, what was the error for the previous quarter, and what was the error 3 quarters ago. And using that, you can estimate what should be the GDP per capita, the quarterly GDP per capita of the UK for the next quarter. And then you apply it again for the quarter after. So this is the simple equation, and your statistical package would have a direct way to do that and forecast, let's say, the next 10 points in time. But if you're not sure on how much can you rely on these forecasts, then a way to calculate or compute the accuracy of these forecasts is that, let's say, if we have data from 1955 to 2020, just don't use that first, but use data from 1955 until 2015 and forecast the next year. Because if we forecast the GDP per capita for 2021, we don't have something at hand to measure the accuracy of it. But if you use in your model data just, let's say, until 2015 and forecast 2016, you have actual results of 2016, and you can compare those actual results with your forecasted results. And the difference of that is forecast errors. It could be above or below. So your forecast might be above the actual, your predictions might be above the actual or below the actual, positive or negative. When you square them, then they all become positive values. So we are looking at the squared errors because we don't really care about if your prediction was above or below. But what we care more about is that how far was your prediction from the actual results that happened in 2016. Let's say we also have actual data for that, but we don't include it in our model so that we can compare our predictions with that. When you square those and take the average of those squares, what you get is a term called mean squared errors. We're not going to go into detail of that, but that is just one way to compare forecast errors and accuracy of your forecast across different univariate models in your quantitative data analysis. Thank you. Next Tuesday, we will look at multivariate time series. We'll start off with explaining spurious regressions and why we need to conduct and use techniques such as co-integrations or use short-term VAR models and so on. And why is a multivariate time series very different from panel data analysis? Because when we have spurious regressions, let's say you are looking at the relationship between three variables, and all three are growing together with time, but they may not have. Let's say if you have a graph like that, the one below, and these three variables might not have any association with each other, but if they're all growing together with time, your regressions are going to show statistically significant results. But we would call them spurious regressions because they have no actual meaning. So what kind of techniques can you use to actually find out if, even if they're growing together in time, are they actually really related? As a bonus, we will also look at the Granger causality test and the argument that correlation does not equal causality. So how can we find out if there is causality? Thank you.